Okay, so 5.4 log functions. You can see we've got 3 different learning targets. Okay, so we can switch. I can switch between logarithmic and exponential notation. I can calculate the domain of a log function. And finally, I can graph and solve logarithmic equations. So we've got, a pretty busy day. And undoubtedly, I think what is going to happen is, kids will look at a log equation and understandably say, what is that? It looks brand new. It looks very different. The log function with base A must be greater than 0. A cannot be a negative value. A also cannot be 1. In other words, A could be a fraction, though. It could be something like 2/3, but it's positive values. And it's read the log to the base of x. And you can say, well, what is that? You can see I actually wrote it a little differently. This is called the log circle definition. The log circle definition. If we go down to the base, you can say this is a to the y power equals x. What we're seeing is this is bidirectional. A logarithm is an alternate way to write an exponential expression. That's all it is. There's more, as we'll talk about functions in just a little bit. But rest assured, what we're going to be able to also note is that the interior, called the argument of a log, it must be non-negative. It cannot equal 0. It must be positive. X has to be greater than 0. Guys, I'd actually like to jump down to these problems first. We'll backtrack in just a little bit. Change each log statement to an equivalent exponential statement. What you need to do is plain and simply use your log circle. You will get a to the 5th equals 4. Guys, you're done. That's all you have to do. You can say over here, e to the negative 3rd, set that equal to b. Here, 3 raised up to the c would equal 5. So those expressions, those equations really could be written differently. Yes? Well, we're going to get to that as we look at, a question is, why can't A equal 1? The problem is, when you think about it, 1, if 1 was down here, let's just hypothetically say it was, and let's just say we had x and y, we would have 1 to the y would equal x. And if you think about it, 1 being raised up to any old power would be always going to be equaling 1. So we're going to avoid that conflict with the exponents. We're not going to have our logarithms deal with a base of 1. Okay? So we're just going to ignore that. Exclude that if you would. Here's another thing that we can definitely always note. The base of the log is the base of the exponent. So the base of the log is also the base of the exponent. So what you're going to be able to do is work backwards. As soon as you look at this first group of problems, yes, you've got a power in play, but you also have this base here. The base is always going to be the base of the log. So we're going to have the log of 1.2 down here. For this problem, we're going to have the log base e. We'll talk about that in just a moment. And then right here, we've got the log of base a. We know we're going to have that always. The actual exponent, however, is never going to be inside of the log. It's always equal to the log. And you can always confirm, even though we're not drawing out the immediate log circle, we could, in just a heartbeat, check that this is right with that log circle definition. right? And you come over here, you'd say, well, my power is a b. You can write b over here. This would indicate e to the b equals 9. And then over here with a power of 4, we put our 4 outside. Let's bring that back over here. And the missing component would be over here. We could check with our log circle that this is right. A to the 4th is equal to 24. Now, I heard someone say just a moment ago with the first one with B, someone said, ooh, log base E is really natural log. The cool thing is you guys learned this before. Natural log of x is really the log base E of x. And you can see that natural log button on your calculator. It's right next to the 4. Okay, but this is just our first learning target, going between the two systems. Going between the two systems. Now, look, finding exact values, you could definitely say, let's call both of these some variable. Let's just call it x. You could call it whatever you'd like. And again, logs can be newer for kids. They can look at that and say, log base 2 of 16. Wow, how do I know what that is? Do a log circle. Do that definition. What would we get doing a log circle? Help me out. 2 raised up to the x equals. Now what you do is you just solve by inspection. You'd say, what number would make that true? 2 to what power would be 16? Answer is 4. And you'd be done. Here we'll do a log circle and we'll say, here we get 3 raised up to the x is equal to 1 over 27. Negative 3, we are going to say. We know that 3 to the 3rd is 27, of course, but to get that reciprocal, we need a negative exponent, don't we? Okay? So as we continue on, let's take a look at the domain. Now, we said earlier that our domain was such that the argument inside must be greater than 0. Not even equal to 0. Greater than 0. So here's what's going on. We could say x plus 3 greater than 0. It only takes you a moment to solve. And guys, that's your domain. You're saying, look, for this log to be defined, for us to be able to work things out here, you can only have x to be larger than negative 3. You come over here to this next example, and my goodness, all of a sudden you look and say, well, now I've got 1 plus x over 1 minus x is greater than 0. Hey, this is like a chapter 4 test question. Some of you are preparing to do corrections, or you're even preparing to do a retake. Here's a great example of an old problem coming back. Let's see, I'd like to know where my denominator could be 0. You could say 1 minus x. Technically, you don't want that to happen, right? You could say, well, x cannot be 1. How about the top? That could be 0. If we just subtract, we'd get negative 1. We have to do a number line. We have to do a number line. Open circle or closed circle above the 1. Open. You're not allowed to equal the 1. How about above negative 1? Open. If you plug in negative 1, your numerator becomes 0. This whole fraction becomes 0. But is 0 greater than 0? No, it's not a solution. So then what? We're going to do some testing. We'll say test, x equals 0. Test x equals 2. Test x equals negative 2. I want to do this quickly. If I were to plug 0 into this original fraction, top is 1, bottom is 1, 1 over 1 is positive. That's true. That's true. That's going to be just like in here, right? And then we could say plug in a 2. The numerator would be positive. Denominator would be negative. Positive divided by negative is negative. Is that greater than 0? No. Guys, if you plugged in a -2, you'd see down below your denominator is positive, your top is negative. That's going to be false. So your domain, now you could write it in interval notation, or you could even write it as an inequality. You could say, look, you can only have x values between -1 and +1, right? And then we come over here to C. You'd say, well, the absolute value right here, wow, that's coming into play. That's coming into play, and this is a trickier problem. Sometimes kids will say, ooh, it's only x is greater than 0. But do you think it would be okay to plug in something like x equals -10? Yeah. You see, really, you'd be saying, I want the absolute value of x to be greater than 0. That's really what's happening. Yes. What's it? No? Oh. No, I'm not. Okay, thank you. Okay, so here we go. At first, I thought we were paused, but no, we're not. Okay, but, you know, at this point, what you can hopefully see is the absolute value of x will give positive output except for what? 0. Your domain, plain and simply, x cannot be 0. This is always true except at x equals 0. Because if you plug in a 0, the absolute value of 0 is 0. We are not allowed to have 0 inside of a log. And if you ever tried it, you'd get an error message. Okay, so we doing okay? All right, so let's go to the second page. And it says graph a log function. What we're really getting at, guys, is this. What you need to know is that logs are inverses with exponential terms. Here's what I'm getting at. Look at the very famous log equation that, you know, we even started the lesson off with. Just y equals log base a of x. And of course, you can change it this way. And you could say, if I did a log circle, I'd have a to the y equals x. And kids would say, well, sure. Well, that is what you'd get if you'd switch x and y for an exponential type of a graph. Think about that. If I gave you y equals a to the x, if I said, now switch x and y, you'd say, well, I'd get this, x equals a to the y. That's really what we have for this logarithm. What we're seeing is a log curve is always going to be the inverse of an exponential curve. And we saw last week that you'll always have a line of symmetry of y equals x. So you could have either of these shapes. If you had y equals a to the x, but you had a being a fraction, you could get this curve. What you're going to see is you'll have a log, type of a graph that's the mirror image, the reflection of an exponent about y equals x. Now, I think the first thing to let you know is that the exponential curve always had an asymptote. What kind of an asymptote did it have? A horizontal asymptote, right? It was always like y equaled 0 or something like that. So what kind of an asymptote do you think we're going to have for a log curve? Vertical. Because x and y switch, don't they? And all of a sudden, instead of having like y equals 0, you have x equals 0. So that's something to really keep in mind. So I'm going to show you how to quickly do some graphs here. And it looks like our video is going to be ending. So I'm going to have to make a new video for the rest of this lesson. And we'll be picking that up later.